Hi, my name is Varun.
My name is Saravanan. We have done a project using myRIO in a way that we can add music using the accelerometers inside the myRIO. What we have done here is we have taken out the wired connections and we have interfaced this myRIO using Wi-Fi. And also we have actually put a battery pack to take out the power connector. We'll now look into the detailed overview of how we can operate this myRIO and get different sounds out of it, and then go on to see how did we actually implement in the LabVIEW platform.
Okay. When I move the myRIO along the x-axis, the frequency changes. So, as you can see, when I move it along the x-axis, the frequency decreases when I move it to the when I shift it to the right, and the frequency increases as I shift it to the left. So you can see the value of the frequency here. Over here. Then as I move the myRIO along the y-axis, the instrument changes. So for the same frequency value, we can have different instruments which can be observed based on the waveform, changes in the shape of the waveform. So if I change it, let's say I put it at a low frequency and I change the waveform, the shape of the waveform changes. I can see the instrument which is playing over here. Now it's on the waveform and float again and on and obey. So this is how we control the frequency and the instrument type with the x-axis and y-axis.
Okay, coming to how we have implemented it, this is the target VI. This is the VI where the input is actually coming in from the myRIO. As you can see here, the input is coming in from myRIO, and when we move the myRIO, is actually changing. So as you can see here, x-axis is 1 and such. So we'll go and look into the block diagram of this. Okay, this is the block diagram of the target VI, whereby the accelerometer values are acquired from the myRIO, and it is actually fed into this scope whereby the graph is generated of the acceleration values. At the same time, it is also taken out and is actually fed to this shared variable, whereby this variable will be actually passed on to the host VI. In this case, it is actually the computer over here. So we'll go on to the host VI. This is the front panel of the host VI. Actually, it's not being played. Okay. So the values that are passed from the target VI is actually coming in to the host VI and is being displayed at this graph over here. This graph is put there so that we can actually know whether the values are being passed correctly and it's the connection between the target and the host is alright. I'll just go on to explain the front panel and then go in and explain the block diagram of this host VI. So as you can see here, the host VI has this input, and this is actually showing the frequency of frequency which is actually scaled from the input frequency, and it is quite a smooth graph. And as you can see over here, this is the output waveform that is being generated, and the output waveform is actually varied according to how you change the orientation of myRIO, as we have shown earlier. And over here is actually the display to tell you which instrument is being currently played. For example, now my friend is actually showing a flute, and when he change it, it's the OB, and when he move it furthermore, flute, and its horn. And other than that, we also have a volume control over here, whereby we can increase the volume and decrease the volume. So over here we have actually just displayed a equation that we have used to derive different instrument, which will be actually explaining later in the block diagram. So we'll now go on to the block diagram. Okay, this is the block diagram of the host VI. As you can see here, the shared variable which is passed from the target VI is actually coming into here to the host VI, and this shared variable is displayed through the graph over here. Other than that, this host shared variable is actually going through some scaling and movement, whereby the initial accelerometer values are from -1 to +1, and therefore we have added positive values over here to x and y axis, and also did some scaling and this is actually used for the control of different instrument as well as frequencies. So the top part is actually used to control the frequency, and the bottom is for the varying the instruments. So at the top, we'll look at it that actually we have put a for loop, if else loop kind of structure, whereby when the frequency is from 1 to 1000, the output frequency is 440 Hz, and 1001 to 2000 it's about 880 Hz. So this is and it goes on actually. So this is to actually differentiate the frequencies in a way that there's different tones being produced. If it's a continuous frequency, there will not be any distinguished tones being produced. So this frequency is being fed on to different sine waves, which I'll explain in a little while. And the sine waves goes on.
It goes. We have downloaded a library called Sound Play Tool. This is from the internet, which enables the lab view to play the sound from the computer's speaker. And what happens here is that we have added multiple sine waves in order to produce a single output, which is played through the speaker.
Again, we have like a if-else structure, whereby we have like 3 conditions, and each condition is actually corresponding to an instrument. So for example, the first instrument is obey, and there are different values being fed to the amplitude of the sine wave. So I'll actually now move on to the equation that we used and reason out why we have actually fed the signal in this way. So this is the equation that we have used to derive different instruments from the same frequency. What is very common here is that the fundamental frequency of this equation, the fundamental frequency is the same. So with the same frequency, you can actually come out with different instruments. With the same fundamental frequency, in each sine wave, the difference is the fundamental frequency is multiplied by 2, 3, 4, 5, and 6, and so on. And as you can see here, the amplitude also varies, and all these are actually derived from the internet. So as you can see here, we found out that these are the amplitude for flute, and each of the different amplitude actually corresponds to different harmonics. For example, this is the first harmonics, second harmonics, third harmonics, fourth harmonics, and so on. So there's flute, there's obey, there's horn, which we have actually implemented. There's actually possibilities of implementing different and more instruments also. So going on to the block diagram again. So as I showed you the amplitude, we have actually scaled the amplitude in a way that the sound can be heard. When we tried out the normal amplitude that we have seen from the website, the sound could not be heard. So therefore there's some scaling done, and the amplitude is being fed on to the sine wave. And for the frequency, we have actually multiplied the frequency by 1, 2, 3, 4, and 5, like accordingly for each of the sine wave. And with the sine wave inside the sound play tone Vi, we are able to get the different frequencies to be played as well as different instruments. So that's about it for the project. We are not what we have achieved is playing different music by varying the frequency and playing in the same frequency different instruments as well. So thank you.
First, I'm changing the frequency for the flute. Now I'm changing instrument for the same frequency. This is obey. As you can see, the frequency value was the same. Then I'm increasing the frequency for obey. Now I'm changing to the third instrument, which is the horn. And changing frequency. Okay. My contribution was to program the LabVIEW. Since I had prior knowledge in programming LabVIEW, I helped to implement this program on LabVIEW.
Okay, for myself, I did work on implementing different instruments in different frequencies, as well as changing the amplitude or different harmonics to get different instruments. So my contribution was actually on the design of getting different instruments as well as changing the frequencies.